Well, welcome. In this video, we're going to be looking at the composition of functions. And you'll recall dealing with composition of functions if you took advanced algebra. A lot of this, what we're going to be talking about today, is going to be review. Some of it will look slightly different from what you saw last year. But for the most part, like I said, a lot of this should be stuff that you've already seen before. Now, to start out with, in this box here, they're illustrating how we write a composition of functions. Now, when you see that little circle, that circle represents the word following. So when you see G, then that circle F, that means that function G is going to follow function F. Meaning the function F, whatever that is, we would apply that first to a value, and then use that answer and apply the first function that's listed there, the G, that's the one that we would apply actually secondly. So when you see that symbol, G following F, means that function F would be applied first, and then function G would follow after that. So we'd apply function G secondly. Now there's a couple different ways that we could see that. Now, one is using the function G following F in parentheses, and then our X, or whatever the value would be after that. Or you see a lot of it just using parentheses. This is the one that I prefer, where we would have G and then in parentheses F of X, meaning that you'd put function F inside of function G. Or the last one, you can see G following F of X, like we have there. So those are three different ways that you could see a composition of functions being referred to. Now, as far as the domain of a composition of functions, we'll get to that in a minute. So I'll actually hold off about discussing that for a little bit. But now there's something that we also learned about in the past called the binomial square theorem that will be really helpful for this lesson. So let's review that over here on the left. So the binomial square theorem, what that's saying is that if you have two terms in parentheses, we call that a binomial, and those two terms in parentheses are being squared, there's a process. It's not just the a squared plus b squared. That's the common mistake that people will make. They'll just write down whatever a is, square that, plus whatever b is, squared, and be done with it. But it's not quite that simple. There's got to be a term in the middle, because what we're doing here is we're expanding it out. Now, if you want to do this the long way, you would take the a plus b squareds, meaning a plus b times a plus b, and FOIL those two binomials together. But again, it's much faster if you just know this binomial square theorem, which would tell us then that you would take the a, that term squared, plus the middle term is going to be found by taking the a and b, multiplying those together, and doubling them. So to find the middle term, you take the a and the b, whatever the first and last term are in your binomial, multiply those two together, and then double them, multiply them by 2. And then the last term will be whatever the b is squared. So that's the binomial square theorem. So you want to make sure that you have that memorized because it'll be useful. We're not going to use it right away in our notes here, but when we get to example 2, that's where we're going to be seeing that theorem being used. So let's start out now by looking at this next example, where we're just going to find the f following g of negative 2, and then we'll find g following f of negative 2, and we'll see if the answers are similar. So let's go now and let's look at those examples. Okay, so this example says that function f is going to be 2x squared plus 3x. What that means is that whatever our value for x is, we're going to square it, and then multiply it by 2, and then add 3 times that value for whatever x is. And g is just whatever x is, subtract 7. So it says we evaluate f following g of negative 2. Remember, another way that we could write this is using parentheses. Now the reason why I like this better is this tells us more specifically what's happening. This means that I'm going to put negative 2 inside of function g. Then I'm going to take that answer and put that answer inside of function f. So again, let's start out with function g. So when I put negative 2 in function g, all I have to do is subtract 7 and gives me negative 9. So that means this piece here is negative 9. So I'm going to put negative 9 now inside of function f. So when I put that inside of function f, I would have 2 times negative 9 squared. Now it's important to remember how to put this in your calculator, because if I put negative 2 in parentheses squared, or I'm sorry, 2 times in parentheses negative 9 squared plus 3 times parentheses negative 9, I can be confident that I'll get the right answer. But if you forget to put the parentheses around the negative 9, if I just type in 2 times negative 9 squared plus 3 times negative 9, this piece here is going to end up being wrong. And so we're going to get this really large negative number, which would be the wrong answer.
So you want to make sure that you put this in parentheses, put the negative numbers inside of parentheses and the square outside the parentheses. And when you do that on your calculator, you get 135 as your answer. So now, why don't you guys try this one on your own? So I'll help you get it set up. So again, this means the same as g following f of negative 2 like this. So I'm going to put negative 2 inside of function f, and then we're going to put that answer inside of function g. So why don't you guys go ahead, take a minute, and work this one out. So pause the video and hit play when you're ready to check your answer. Okay, so this is what you should have got as your answer. You should have gotten negative 5. Again, the way that happens is you put negative 2 inside of function f, and if you plug that in your calculator correctly, you get a positive 2 as your answer. If you got a negative number as your answer, it's because you forgot to put the negative inside the parentheses, the negative 2 inside the parentheses. And then when you put 2 inside of function g, well, 2 minus 7 is negative 5. So that is your answer. And you can see that even though we were using the same two functions, and even though we were using the same number here, negative 2 is our value that we were putting in for x, we got two completely different answers. That's significant, and we'll talk about that in a little bit. Now let's look at this next example. This is where we're going to be working with the actual composition of functions to come up with a new equation. Because here we're trying to find f following g of x. Remember, that's the same as f of g of x like we had before. But there's no number to put in for x here. It just says f following g of x. Well, we're looking for an equation. We're looking for a new formula here. So what we're going to do in this case is we're going to put function g, which is x minus 7, and replace every single x that we have in the function f with x minus 7. Now notice I said that we're replacing x with that other equation, or the other expression, x minus 7. So it's not going to be just 2x squared minus 7 plus 3x minus 7. Okay, you're not just replacing the minus, or not just putting in minus 7, you're replacing x with the whole expression x minus 7. Here, let me write this out so you can see this, what I'm trying to get at here. Okay, so here we have, what I just did here is I replaced the x with x minus 7. So you want to make sure that you're very careful when you write this out, because the way you write it out is going to will determine what your answer is. And if you write it out wrong, you're going to get the wrong answer. Now, order of operations tells us we would not distribute the 2 first. I would first take care of the exponent, which is why we have that binomial square theorem. So you want to make sure that you have this memorized, because you're going to need this, because this is where we're going to start using it for this problem. Because again, you have two terms in parentheses being squared. So we're going to use the binomial square theorem. So I'm going to have the x, when you square that, is x squared. Then I take 2 times a and b. Move this down a little bit here. A in this case is the x. The b in this case is negative 7. Now you're not going to distribute. Don't take 2 times x and 2 times negative 7. That would be wrong. We're just going to multiply these three together. So 2 times x is 2x times negative 7 is negative 14x. And then negative 7, when you square that, becomes a positive 49. We still have the rest of this, though, so we're going to have to distribute the 3 through. So we'd have 3x minus 21, and we still have the 2 in front of here. So we still have to distribute the 2 through, so when you do that, let me move this up a little bit here. When you do that, we get 2x squared minus 28x plus 98. And then plus the 3x minus the 21. So now we're going to combine like terms, and that will give us our final answer. So when I combine like terms here, the 2x squared, there's no other x squared, so it just stays a 2x squared. The minus 28x and the positive 3x, well, negative 28x plus 3x is minus 25x. And then 98 minus 21 is 77, so we'd have plus 77. So this would be our answer. Now, what is the point of this? Well, let's go back to the previous example. Remember, to get my answer here, I had to put negative 2 inside of function g, get negative 9. Take negative 9, put that answer in for function f, and I get 135. Well, now, if I were to take and put negative 2 inside of this equation, I would get directly to my answer. So here's what this does. This makes it, instead of having to do multiple steps to get our answer, the composition of functions is merging together the two functions into one larger function that will allow us to get our answers. So if I had a whole bunch of problems, like let's say if I had f following g of -2, and then I had f following g of 7, and f following g of 13, and f following g of -8, I wouldn't want to have to go through the whole process that I did in an example 1a. I can now take each of those numbers, put them into this single function, and get directly to my answer. So it saves us a lot of work in the long run. Now, you might think, man, this is a lot of work to always have to do. Well, it's not always going to be this much work. The only reason why this one was so much work is I had a binomial being squared. Let's look at part B here. Part B is asking us to find g following f of x. Now watch what happens for this one. Because here I'm going to take this 2x squared plus 3x, replace x in my other function with that expression. So I end up with 2x squared plus 3x, and then minus 7. And guess what? That's my answer. I can't simplify that any further, so that is my final answer. So you can see it's not always going to be as complicated as part A. Let's look at part C here. It says, verify that f following g does not equal g following f by graphing. Well, we're not going to actually look at the graph because you can pretty easily tell here when we look at these two functions, 2x squared minus 25x plus 77 is not the same as 2x squared plus 3x minus 7. So here's what they're trying to illustrate. We have this thing in math called the commutative property. So this is showing us that the commutative property does not work. Now you might be saying, well, what is a commutative property? Well, the commutative property applies to a number of different situations. For example, the commutative property applies to addition. Because essentially what the commutative property is telling us is that the order we do things does not matter. So 2 plus 5 is the same as 5 plus 2. They would both give us 7. The commutative property also works for multiplication. Because 2 times 5 is 10, and 5 times 2 is also 10. But the commutative property does not work for division. If I had 2 divided by 5, that's not going to be the same as 5 divided by 2. And it also is true that the commutative property does not work for composition of functions. That f following g is not going to give us the same result as g following f. We saw that here with our equations, and we saw that up here when we put -2 inside of our equations, we got 135 and -5. So the commutative property does not work when we're dealing with composition of functions. Let's look at this next example, just part A. I'm going to have you guys do this one on your own. Again, I'll help you get started. But I want to make sure you know how to use the binomial square theorem. So here we're trying to find f following g of x. So this time I'm going to put this piece in here for x. So it's going to be 1 divided by 3x plus 1 being squared. Now whenever we have a fraction being squared, the numerator gets squared and the denominator gets squared. Well, when you square 1, you just get 1, so that's not a big deal. But I want you to square the 3x plus 1. I want you to apply the binomial square theorem and simplify the denominator here. And so pause the video and hit play when you're ready to check to see if you have the correct answer. Okay, so you should have gotten in the denominator 9x squared plus 6x plus 1. Now, for some reason, a lot of times people have a hard time trying to figure out, well, what is that middle term? So here I just want to show you how we got that 6x. So again, your binomial square theorem tells us to take a squared plus 2ab plus b squared would be your answer. So how do we get the middle term? Well, the middle term, we take 2 times the value for a, which is the first term in parentheses, times the value for b, which is the second term in your parentheses. So here we have our value for a would be 3x, our value for b would be the 1. So we would take 2 times our value for a, which is 3x, times our value for b, which is 1, and together those multiply together to be just 6x. So we'd have 9x squared plus 6x plus 1. Okay, let's talk now about how to find the domain of a composition of functions. And then we will end the video there. But there's still one more part that you want to make sure you know how to do, which is a composition of transformations. So I'll have a separate video that'll show you how to do that. Now, remember from the beginning of our notes, let's go back up there. There is this sentence here that talks about the domain of the two functions. The domain of g following f is a set of values of x in the domain of f for which f of x is in the domain of g. What in the world does that mean? Well, here's what this is telling you. First, when you're trying to find the domain of a composition of functions, again, we do it in the order we're supposed to. It's g following f. So we start with function f, and we look at what's the domain of function f. And then what you do is you put function f inside of function g and figure out, well, does that domain, is there anything else that we need to include or not include in our domain when we go and look at the composition of the two functions? Here's what I mean. Let's look at this particular example, where we have function f is the square root of m. Function g is 2 divided by m minus 3. Let's start out with function f. Function f, here we're trying to take the square root of m. I want to find the domain of that. Now, recall from taking roots of numbers, I do not want to take the root of a negative number. So I want to make sure that my values for m are not going to be negative. So that's the first thing I'm going to consider, is that m can't be negative. Okay. Now, do not treat these as two separate pieces. The reason why I'm starting out by looking at just function f is because we're trying to find the domain of g following function f. So our theorem tells us that we have to look at the domain of function f first. So the domain of function f is that m can't be negative. Now I'm going to consider the composition of these two. G following f means that, or g following f of m, let me write it like this, means that I'm going to take the square root of m and put that in here for m. So instead of 2 divided by m minus 3, it's 2 divided by the square root of m minus 3. So I already know that m can't be negative. Now when I find the composition of the two functions, is there anything else that I need to eliminate as far as my domain is concerned? Well, remember, we can't divide by 0. So the other thing that m can't be here is m cannot be 9. Because the square root of 9 is 3, and 3 minus 3 would be 0. So m also can't be 9. Now, I don't want to always write this out in words, so I want to have a shorter way to write this. So that's what we use the set builder notation for. So anytime we're dealing with a set, we have these brackets, and everything inside the brackets are referring to the set of numbers that we're working with. So we're working with the domain. So in our domain, we're looking at our independent variable, which is m. Now, it's not going to be everything in m. It's not going to be all real numbers. So there's going to be a limit that we have to put on this. So we have this bar. That bar refers to the word such that, or I should say the words such that. Now, we could also use, instead, we could also use a colon here. So if you ever see this instead, it means the same thing. It's a colon, by the way, not a semicolon. So be m such that, but I like this line. Now we're going to, following the such that, we're going to put our limits on it, saying that m can't be negative. So the way that we write that is we say that m is going to be greater than or equal to 0. We wouldn't just say m is greater than 0 because we can include 0, because I can take the square root of 0 and just get 0. So that's fine. So m is going to be greater than or equal to 0, and m can't be equal to 9. So we'd say m is not going to equal 9. And this would refer to, this would be our answer, this would be our domain. It would be the set of numbers where m is going to be greater than or equal to 0, and m is going to be not equal to 9. So let's look at the next one. So we want to find, again, the domain of f following g. So the way that this is written, I want to focus on function g first. So when I focus on function g first, I look at this equation and I see that, well, in function g, g can't be, g is not going to be negative 1/3, because 3 times negative 1/3 plus 1 would end up giving me 0. Now, I might say, well, I couldn't do that in my head. So here's how you can look at that. We don't want to have 0 in our denominator, so here's what I'm doing. I'm going to say that 3x plus 1 equals 0. I want to figure out what would x have to be to give me 0 as my answer. Subtract 1 from both sides, and I get 3x equals negative 1. Divide both sides by 3, and I get x equals negative 1/3. So I know in my equation here that x can't equal negative 1/3. Now I want to see, is there anything else that I have to put a limit on? So I want to find f following g. Well, what that means is that I'm going to put function g, which is this whole fraction, inside of here for x. So it'll be 1 divided by 3x plus 1, that whole fraction being squared. Well, technically I can square any number, so it doesn't matter what this is. So really, so nothing's going to change here. So as long as x is not negative 1/3, everything will work out. So that's my answer for my domain, is that it's x is all real numbers such that x does not equal negative 1/3. Okay, so we're going to stop the video here. And in the next video, we're going to be looking at how to find the composition of functions. So make sure that you take the time to also watch that particular video if you need to.